I'm going to explain exam type problem number 1. First, we are going to see the description. Within a manufacturing process, we can say that pieces exit the warehouse and arrive the production floor following a Poisson distribution of 5 per minute. The first process for these pieces is a quality check where experience says that we reject 2% which are being considered waste. Then the pieces are divided equally into 2 production lines. The first line takes the following steps: grinding with an exponential average time of 5 minutes, assembly with a normal distribution behavior with the same mean and the grinding and variance of 4 minutes. In the second line, we perform the same activities, but the grinding is normal with mean of 5 and a standard deviation of 3 minutes, and an assembly has a uniform behavior with mean of 5 and variance of 5 minutes. Later, parts of both lines go to a final quality control where historically we reject 1%. At the end, the finished product occupies a space of the warehouse for approximately 7 hours. The final warehouse has a capacity to store up to 1,000 items at the same time, and we believe that at the beginning of the simulation is empty. We need to answer, is there a need to increase the capacity of the warehouse? How many more spaces? And what process would you consider the bottleneck? This diagram represents what we just said, and it simplifies a lot the description. First of all, we have a warehouse where the pieces arrive, and they arrive from this warehouse to the main production floor. They arrive with a Poisson distribution of 5 pieces per minute, and this is an exponential distribution of 0.2 minutes per piece. Then they come to an inspection where 2% of them are rejected and they exit the process. The remaining 98% divide in 2 lines. We expect this dividing being 50% for each line. In line 1, there's a rectification with an exponential time of 5 minutes, and then they come to an assembly and then with a normal time of 5 minutes as a mean and 2 minutes as a standard deviation. In line 2, we have a rectification with a normal time of 5 and a standard deviation of 3, and then an assembly of a uniform distribution with a mean of 7 and a standard deviation of 3 minutes. Then the pieces of both lines come to a final inspection where only 1% of them are rejected and they exit, and the 99 remaining pieces go to a warehouse where it said that occupies a space of this warehouse for approximately 7 hours. Well, then comes the solution, and I'm not going to read this solution. I'm going to close this presentation, and I'm going to start from the beginning in the software to explain it one line at a time. Let's end this, and I'll keep PowerPoint open to see the diagram. And I'm returning. So first of all, we have an exponential distribution that it's already defined, the normal distribution and one normal variable, but we need one assembly and one rectification. So we need 2 normal variables. I'm going to change the standard deviation of this variable. This 300, I'm going to change it for 2 minutes, and the mean to 5 minutes. I'm going to copy this line and paste it right here. I'm going to change the name, and the other normal variable has a mean of 5, but a standard deviation of 3. Okay. For this example, we are going to assume that the lines or the queues are infinite, and I'm going to explain you later why is that. So we are not going to have any storages. So we are going to generate transactions every 0.2 minutes and a standard deviation as an exponential distribution. Okay? This is the arrival process, this part right here. Then we are going to reject 2%. So I'm going to say transfer, capital letters, transfer 0.98, and I'm going to continue 1, and the rest, the 2%, to exit 1. Exit 1 is going to be terminate, just terminate without the number 1. So when we have a start, we don't use these exits to decrease that start. Continue 1 is going to be another transfer. It's going to be right here, and it will be a transfer of 0.5, another fractional transfer of 0.5 for line 1 and another 0.5 for line 2. Transfer 0.5 to line 2, line 1. Line 1 is going to be this part of the process right here, and it will be Q line 1, then sys rectification 1, depart line 1, advance a time of 5 minutes with a standard deviation of an exponential distribution. Then we release rectification 1, and we are going to enter to another queue, a queue before the assembly line or the assembly operation, queue line 2, sys assembly 1. Well, that was kind of curious. That's better. Assembly 1, and we're going to depart line 2. Then it's the advance of a normal distribution, and for this we are going to need the first variable. So it's going to be a variable called dnorm. After this advance, I need to copy that diagram. After this advance, it's going to be a uh, release assembly 1, and it's going to, I'm going to use an unconditional transfer to a line called continue 2. For this is going to leave us right here, right before the final inspection. And I'm going to return to program line 2 of production, the second rectification and the second assembly. I could copy this, but I'm going to explain it line by line. So in line 2, we're going to enter to another queue. This is going to be Q3. Our queue is going to cease rectification machine or process 2. It's going to depart line 3. After departing line 3, it's going to advance. Let's get into the diagram. It's going to advance with the second variable. Tap here and a variable name dnorm 2. Then we are going to release rectification 2, and we are entering the last queue, queue number 4. We are going to cease the assembly 2. Then we are going to advance and uniform time of 7 with a standard deviation of 3 minutes. We release the assembly number 2. After this, we are going to transfer to count number 2 for continue number 2. Then in continue number 2, it's going to be, this is not written, okay. It's going to be a transfer of 0.99. This is going to be an exit 2 and continue number 3. Exit number 2 is going to be a terminate without a 1, and continue number 3 is going to be I'm going to need an storage. I really need an storage for this warehouse, so I return to the definition part of my program. I open a line right here and I call this warehouse warehouse with storage with a capacity of, let's say, the program says something about that. Let's see. The final warehouse has a capacity to store up to 1,000 items. So we really need this storage of 1,000. I'm going to copy this name. And first of all, if I want to know how many more spaces I need in the warehouse, I'm going to put a cube right there. And it's cube number 5. And then I'm going to enter the warehouse. Then I'm going to impart line 5. I'm going to advance it 7 hours. Yeah. So 7 times 60 is 420. And we are going to leave the warehouse and terminate 1. I'm going to save this. Then let's create the simulation. It is ready. And let's begin this ride. If we want to put the warehouse to test, we need to give the program a start that does this. So I'm going to give a start of 2,000. And it marks an error. It has a problem with gnorm variable number 2. It says here that it has a negative time increment. Why is this? Let's return to the program. The norm variable number 2 is the rectification in line 2 of production. And this is because we have a mean of 5 and a standard deviation of 3. If we know the concept of a standard deviation, we know that it's the average between every value and its difference with the mean or the average of the distribution. So these standard deviations comes from an average of a variance between every value and the mean of the distribution. This is this 5, a variance between this 5 and every value of the distribution. So being these 3 an average, there could be numbers up from 3. Let's say these 3 can come from average 6 with 0, a variance of 6 with a variance of 0, and when you add or rest 6 to 5, this becomes negative. So the advance is advance minus 1. And if you tell the program to advance minus 1, this is why you have a negative time increment, because the variance of the value, the standard deviation, it's greater than the mean. So when it rested, becomes a negative time, and it cannot execute this negative time. So in terms of our program, what we need to know is, can we change the standard deviation of gnorm number 2? Can we change these 3 to become less? Can we change that in a process? Think about it for just a second. The main boolean in a process is variance. So as an industrial engineer, you need to be thinking of your nemesis is variance. So you're going to work with processes where you are going to need to decrease this variance. So yes, we can, but we need to work with the process. We need to improve the process, change the methods, change the technology. So we can come here to our program and say, okay, I got a standard deviation of 1. So I'm going to run this and let's see what happens. Okay, it says here that it doesn't understand this work. Let's return. It's missing an H. Okay, this is great. We create the simulation again. We start, and then 2000. And now we have the negative time increment problem in variable G norm. As I explained it to you, this comes because of the standard deviation. It's a big standard deviation, so we need to change this. But in order to change this, we need to change and improve the process. This is the easy part. I save this. I create the simulation. I start 2000. Okay, I have my results. And then time of 6,481 minutes. And these statistics right here. So let's go to the presentation and let's see what it says here. Is there a need to increase the capacity of the warehouse? Let's see. I put line 5 to do that work. And I have a maximum content of 1 and average count of 0, an average time of 0. So it seems like we don't have a problem with the final warehouse. The second, how many spaces? The answer to this is 0 more spaces. Is there a need to increase the capacity of the warehouse? No, there is no need to increase the capacity of the final warehouse. The final question is, what process would you consider the bottleneck? And this is where this becomes interesting because we have to analyze the problem real good. So where do we find the bottlenecks? The bottlenecks are in the queues that we put before every process. And for every line, from line 1 to line 4, there are maximum contents of a lot of pieces, all but line number 3. But if we see, the main problem or the main problems are in line 1 and line 3 with this amount of pieces waiting to be attended. Line 1 and line 3, returning to the diagrams, are the lines before the rectifications problems or the rectification processes. So the bottleneck of our process are the rectifications in each line. Once solved this problem, we expect the bottleneck to move to the next process. But just to answer that question, the bottleneck are the process that provoke the creation of the lines, of the queues. So this amount of pieces are waiting to be attended. But let me ask you just one more question. Where are these pieces waiting? Are there really queues in factories? Do we have capacity to store 7,200 pieces just right before a machine, or they are waiting somewhere else? Think about it for a second. Where are they waiting? Well, as we are not in class, I'm going to answer this right now. They are waiting in the first warehouse. In this warehouse right here, we have some 14,000 and something of pieces needed to be produced, but waiting to be produced, waiting to be in these two processes. They need to go to the rectification process, but they are not needed. And we don't see this. We just see a factory that it's working at the full of its capacity, and we think it doesn't have any problems. And we really do have a problem. So in conclusion, in this problem, these were the questions, but we need new questions. We need to find the real problem, and the real problem is not the capacity of the final warehouse. It's the capacity of the first warehouse. You need a capacity of more than 14,000 pieces in that capacity. And I assume if the capacity of the final warehouse is 1,000 pieces, the capacity of the first warehouse is equal to this. So we need 14 times more capacity of this warehouse. And this is the end of exam type problem 1. I hope this video helped you to understand this. If not, please come to my office and to give you some advice. Okay? Bye-bye.